Alright, so this is Multivariable Calculus, Lecture 3. Today the goal is to do cross products. How many of you... It's giving me interesting warnings. I hope the new equipment arrives quickly. How many of you have seen determinants before? Okay. You are not required to have seen determinants before. If you have, it will make a lot of this material easier. So as a rule of thumb, if I ever need material from a class, it's either real analysis to make things rigorous or linear algebra to give us a good formulation for looking at things. What I want to do is I want to try to explain what the cross product is, what the formula is for computing it, why we care about this. And to do a lot of this, it really helps to know linear algebra. And so the big thing we want to start with is systems of equations. So in linear algebra, you might have seen like ax plus by equals u, cx plus dy equals v. And the question is, how will we solve for x and y? So one way is the method of substitution. I can take the first equation, I can solve for, say, x in terms of y, substitute into the second, solve the second for y, and then solve back and get x. You can also write this down in matrix form. A, B, C, D, acting on x, y, gives you uv. And then there are techniques in linear algebra to go through the algebra and come to a solution. The idea is to find a good way to do the steps to increase your likelihood of getting to the answer quickly and easily. The question is always, what are the solutions? How many are there? How can I find them? So the first thing is, do solutions exist? If the answer is no, then there's no need to try to find them. If there are, how many are there? And if you know that there are a certain number, can you find them? So let's say I give you x plus y equals 4 and x plus y equals 8. Right? Kim and Kayla, you might even be able to answer this. How many pairs of x and y add up to 4 and add up to 8? Well, I want choices of x and y that will add up to 4, and those two numbers also add up to 8. Are there any numbers that do that? No. Because if x plus y adds up to 4, can it add up to 8? No. So x plus y equals 4, this is the equation of what? A straight line. And x plus y equals 8 is also an equation of a straight line. They're parallel lines. They have different intercepts. When x equals 0, y equals 4. When x equals 0, y equals 8. So if I were to draw it, here's 4, here's 8, I would have two parallel lines like this. Two parallel lines will never intersect, so this will have no solutions. If I do 2x plus 2y equals 8, how many solutions are there now? So x plus y equals 4 and 2x plus 2y equals 8. How many solutions are there now? Infinitely many. Once you solve the first equation, you automatically solve the second. So it turns out there's a really nice condition as to when a system of 2 by 2 equations has a solution. It comes down to, is the determinant non-zero? And the determinant of a 2 by 2 matrix, so the determinant of the matrix A, B, C, D, we often write that as A, B, C, D with big vertical lines, is AD minus BC. I can define anything I want in mathematics. The question is, when is this useful? It turns out that this equals the area, or better yet, the signed area of the parallelogram generated by the vectors AB and CD. And this is eventually going to lead us into the cross product. So I will start off now with the definition of what the cross product is. It is a painful definition. Let's get it out of the way now. So the cross product. All right, so V cross W is going to be a vector. And it's defined as follows. It's going to be, oh, here, let me just write it explicitly. So V will be V1, V2, V3. W will be W1, W2, W3. V cross W is the new vector V2, W3 minus V3, W2 as its first component. Its second component is V3, W1 minus V1, W3. And its third component is V1, W2 minus V2, W1. So this is the cross product. You either have to memorize this, or you have to memorize the other formula that I'll give you later in class. But you need one of these two ways to compute it. Now, programs like Mathematica can compute stuff like this for you. The only thing you have to be careful about is that you make sure you define your quantities with the right labels. So you might think you're defining a vector, but you might have accidentally defined a list. And then Mathematica might interpret things incorrectly. So you've got to be careful with stuff like this. All right. So this is the place where some kids can earn some things back. This is V cross W. I'm going to say two facts about V cross W. V cross W is perpendicular to V and W. And the second one is V cross W is equal to negative W cross V. Any thoughts as to how we could prove these? How might we try to prove these results? So proofs. Dot product and algebra. Is it enlightening? It's just you do this calculation, and after the algebra, 0 comes out. So if there's time at the end of class, I will talk about my record for the longest proof of Morley's theorem. My proof is about 48, 49 pages. The best proof is about half a page. It is a very long, tedious calculation. It is unilluminating, but it gives you the result is true. If at all possible, we want to avoid that. But it's nice to know the result is true. We can take the dot product. And so all you would have to do is do V1, V2, V3, dotted with blah. V2, W3 minus V3, W2, dot, dot, dot. And then just do the algebra and get 0. Similarly, for the second, also plug and chug. Just calculate W cross V, multiply by -1, and show that it equals V cross W. So again, plug and chug. I'll try to give very soon a more geometric meaning to what's going on and a more geometric interpretation as to why this is true. But it's at least good to know that we have these results. So it turns out the cross product, it's defined to be a vector, which is great. A vector has magnitude and direction. And for the cross product, both of them are important. The magnitude is the area of the parallelogram spanned by V and W. And the direction is perpendicular to the plane of the two of them. So this is a multivariable calculus class. What were you expecting to see in a multivariable calculus course? Which we really haven't done so far. I'm sorry? Well, we've seen multiple variables. What would you expect to see in a multivariable calculus course? Derivatives, integrals, stuff like that. We're not doing any of that, right? We're doing all this stuff on vectors. Why are we spending all this time on vectors? We're establishing the notation. when you generalize from one dimension to higher dimension, it's not often clear what goes on. The big idea in one-variable calculus was if I give you a function, you can replace it locally with a tangent line. If I have a function of two variables, rather than replacing it with a straight line, what do you think we replace it with? A plane. And so we're going to need ways to talk about lines and planes. And that's why Friday's lecture will be on lines and planes. The nice thing about the cross product is this will give you a normal to a plane. So if you have a plane with v and w, the cross product gives you a direction perpendicular to that. Or another way of saying it is, if I give you that cross product, I want to try to find maybe the plane that has that as the normal. So we're really building up material that we can then use for later investigations for calculus. So the calculus is coming. Right now, the trouble, it's turning a little bit more, come on. Okay. All right. So I gave you the formula to calculate the determinant of a 2 by 2 matrix. It's just AD minus BC. And you can check and go brute force and see that it's the same. That if you flip these two rows, you get the opposite of this. It turns out this is the signed area of the parallelogram. So if I switch the order of the two vectors, it switches the area by -1. Okay? This is very similar to a lot of other things where order matters. If you think back to Calc 1, Calc 2, when you calculate integrals under curves, it's positive if it's above the x-axis, it's negative if it's below. A lot of quantities are signed. This is another signed quantity. If I give you the vector AB, and I want to find the area of the parallelogram spanned by AB, and I have one other choice for my other vector, what would be a really good direction for the other vector to calculate the area of the parallelogram, where you can do it immediately? You don't even need to know if that formula is true. Same direction. If CD is in the same direction, it's going to be really easy. And if you think about it, so here's AB. Let's say it's R times A, R times B. Then the determinant would be ARB minus BRA, which would be 0. So the formula at least works in the special case when one vector is a multiple of the other vector. The next question is, what happens if we have two vectors that are not parallel in the plane? Do we get the area? So the first thing we need to do is figure out, how do you find the area of a parallelogram? And so I know one of my kids who is in 3rd grade recently had homework where she had to find areas of parallelograms. So let's assume the parallelogram looks like this. Okay? What's the area of a parallelogram? Do you remember? Yes? Okay, so this is the base. And do you want this line, or do you want a different line? Which line do you want? Which line? Oh, is this the line you want? Trying to guide my daughter. Do you remember what we call that? Height. So the question is, why is it base times height? Right? We know this is true for a rectangle. Anybody know how you would prove that it's base times height? So let's think about what's going on. Let's call this angle theta. Let's extend this line over here, and we'll extend the line down here. We love right triangles, right? Always think back, we're the politician. It doesn't matter what question you ask us. I'm going to work it to something I know. I know how to work with right triangles. So where might I want to drop a line in this picture? Yes? Straight down. To which point? To where theta is. So I could drop one line there. Is there any other line you might want to drop?
Straight down from the dotted line.
Straight down from where?
The dotted line.
This line from here?
No, the dotted line.
Right here?
Yeah, right at the top.
Right here?
Yeah.
From here down? So this is one possibility to drop from there. That's actually a little bit too far. It's better to drop it from here. The reason is, if this is theta, this angle here is theta. This angle here is theta. Or if you want, this is theta, this is 90 minus theta here, this is right angle, this is 90 minus theta. Look at these two triangles, this triangle here and this triangle here. So this would be 90 minus theta, theta, and a right triangle. So for these two triangles, they both have an angle theta, they both have the same height, they both have the same hypotenuse. And now you have to remember all those different combinations of the letters A and S for when two triangles are equal. The profane word is not possible, but side angle side works. And so for this, side angle side, side angle side, these two triangles are equal. So the area of this triangle is the same as the area of this triangle. So I can snip this triangle up, put it down over here, and now I just have a rectangle. And there's the base, and there's the height. And this is why the area of the parallelogram is base times height. This was the scissors proof we did, Kayla, where we just chop this off and move it over here. OK. So now the question is, how do we interpret this in terms of the quantities that come into play in our proof? When we did the dot product, we started off by assuming one of the vectors was in the direction of the x-axis. That makes things as easy as possible. Let's build intuition again. Let's assume the first one is in the direction A0, and the second one is CD like this. And so now we want to calculate the area of this parallelogram. How would we calculate the area? So what would the area be?
Start by drawing a height of D.
Yeah, the height is just D. The base is just A. So the area is just AD. So our claim that it's AD minus BC, it still looks reasonable. It's giving us the area in the special case of a parallelogram where one vector is oriented along the x-axis. If we knew linear algebra and if we knew rotation matrices, we could actually then pass to the general result. We do not know that. Please take this as yet another reason why you should continue and take linear algebra. And then you can avoid having to do a lot of these painful calculations. Okay? We're now going to try to prove in general why formulas like this are true. All right. So let's say I have a vector v and I have a vector w. And I want to calculate the area of the parallelogram. What do you think I should take for my base? V. You could do W, but then you'd be going against centuries of math tradition. So we'll take the base to be V. What would the height be? Well, V minus W would be the line going like this. Oh, sorry, you said V minus W? Yeah. That would actually be the line W minus V. So it's not V minus W. The height is going to be the length of that line. How would I find the length of that line? Yeah, so I have to add in a theta over here, and it would be the length of W times the sine of theta, and this would be the area. It's actually going to be a signed area, Because because the sine of theta could be negative. Have you seen anything close to this before with vectors? Anything involving a theta? Where have we seen this? Yes, but what do we get from the law of cosines? But I want something with vectors. So we use the law of cosines to get to this result. So you're very close. It's the dot product, right? So again, we are the politician who does not want to honestly answer the question that was asked by the reporters. We want to somehow convert this to what we know. We know cosine theta. We have sine theta. How can we get from sine theta to cosine theta?
Square, and then square both sides, and then you change sine theta.
Good. Sine squared plus cosine squared is 1. So sine squared is 1 minus cosine squared. And what's really nice about squaring things is that we don't have to worry about, is it the signed area anymore? If you square it, it's definitely the area. So we get area squared is the length of v squared, the length of w squared, sine squared theta. So that's the length of v squared, the length of w squared, 1 minus cosine squared of theta. Okay? And now we do more algebra. So what should we do at this point? So what do we do now? So area squared is length of v squared, length of w squared. And what do I replace cosine squared with? Yes?
P dot Q over.
Okay, can't be P dot Q. You're close. I can. So, because we don't have P's and Q's here, so what should it be? Yep, V dot W over but now we need to square it because it was cosine squared. So now we get the length of v squared, the length of w squared, minus v dot w squared. Okay. Now what do we do? This is where you roll up your sleeves and you do the algebra. So Cam, this is the algebra that if you do, you get the iPad back. So I will show you. So you will have to calculate v1 squared plus v2 squared plus v3 squared times w1 squared plus w2 squared. No, w1 squared plus w2 squared plus w3 squared minus v1 w1 plus v2 w2 plus v3 w3 squared. And after you do algebra, it turns out this is the same as v2 w3 minus v3 w2 squared plus v3 w1 minus v1 w3 squared plus v1 w2 minus v2 w1 squared. So if you expand these and show that they're equal, you get it back.
So I can't just say they're equal?
Nope. You have to do the algebra. Who wants to do the algebra? Who wants to look at the book and see it there? So you need to do this algebra once in your life. Anybody recognize what this quantity is here? Close. It's related to the cross product, so it's v cross w What's its relation to V cross W? So these are the components squared of V cross W. What's the sum of the squares of the components? Not the length, because it's the sum of the squares. If I had the square root, it would be the length. So because I don't have a square root, it's not the length, but not the area of a vector, the length squared. So this is the length squared. So it's not horribly painful algebra, but it's not pleasant algebra. What this tells you is that the magnitude of V cross W is equal to the area squared. And if you think about this, this formula has a lot of nice components. If I'm trying to calculate the area, if I triple V, I should triple the area. And you see that because here everything is going to depend nicely in that regard. When you look at the components here, if I triple V, each of these components gets tripled. The more challenging part, the harder part, which several people had asked me about, is how do you notice that this is in a perpendicular direction to V cross W? How do you notice what direction this vector is in? And this is where it would really help to know linear algebra. Since we don't, I'm going to try to, yes?
You said that's a length squared, but doesn't all of that come up to equal your area?
Yes. So, I thought you were talking about the area of V cross W. It's the area of it's the square of the area of the parallelogram spanned by V and W. So you've got to be very careful. V cross W is a vector which has length. And so in terms of the units, this would be like meters squared. So we've got to be extremely careful about what things would be. But since we're not taking cross products, if this is meters and meters, this would be meters squared. This would now be meters to the fourth. So this would actually be meters to the fourth. So in terms of what are the units of V cross W, it can get very interesting. So if I looked at the vector V cross W, it is the square of that length. So what I want to do now is I want to show you a quick mnemonic to calculate the cross product. So you don't have to remember this is the formula for the x component, the y component, and the z component. How many of you have seen the trick for 3x3 determinants? Okay, good, a fair number. So this trick only works in the 3x3 case. It does not work higher. Think of the 16 over 64 that we did, or the 19 over 95. It sometimes works, it doesn't always work. What you do is you write down A, B, C, D, E, F, G, H, I. And you want to calculate the determinant of this 3x3 matrix. The way you do this is you write down the first two columns again, A, D, G, B, E, H. And you multiply diagonally. And when you go down, those all come in with a plus sign. Then you multiply up, and those all come in with a minus sign. And so you get the determinant is AEI plus BFG plus CDH minus GEC minus HFA minus IDB. So this is just a really good way of remembering the formula for a 3x3 determinant. All right, what we're going to do now is something extremely illegal. When you calculate a determinant, you normally put in 3 vectors. And it turns out that when you develop the theory of the determinant, you see that it gives you, in 2 dimensions, the area of the parallelogram spanned by your 2 vectors. In 3 dimensions, it gives you the volume of the parallel pipehead spanned by the 3 vectors. In 4 dimensions, it gives you the hypervolume of whatever you would call that, and so on and so on and so on. So what we're going to do is for the cross product, V cross W is equal to the determinant V1, V2, V3, W1, W2, W3, Then here's the part that's a little bit illegal. I'm going to put in the first row the unit vector in the x direction I, the unit vector in the y direction j, and then the unit vector in the z direction k. This is illegal, right? I have a determinant where some of the entries are numbers and some of the entries are vectors. But it's a good mnemonic. It will lead to the right answer. And then I'm going to replace the vectors I, j, and k with numbers and give you a geometric interpretation for what's going on. So here, let's write, here's I, here's j, here's v1, here's w1, here's v2, and w2. I'm going to now calculate the 3 by 3 determinant. Will you allow me to save time, and rather than just drawing all the pluses and all the minuses, let me just collect terms. Let me collect all the terms that have an I together. Let me collect all the terms that have a j, all the terms that have a k. How many terms will have an I? Yes. 2. Excellent. How many of them will have a plus sign?
3.
Well, there's 2 terms. Of those 2 terms, how many of those 2 terms have a plus sign? And how many have a minus sign? 1. So if you look over here, I, v2, w3, that will be the plus sign. This one will involve j, this one will involve k. If you go this way, that involves k, that involves I, that involves j. For the i's, 1 plus, 1 minus. Okay? How about j? 1 plus, 1 minus. How about k? 1 plus, 1 minus. So when I multiply this out, here's my I term. I will get v2 w3, and then the minus 1 will be v3 w2. And the j term will be v3 w1 minus v1 w3, and then the k term will be v2 w1 minus v1 w2. So that is a nice way to remember the formula for the cross product. Okay? So again, this is not a standard determinant. Now, I've claimed that the geometric interpretation of v cross w is it's the area of the parallelogram spanned by v and w. Let's assume life is simple right now. Let's assume v and w are in a plane. And so they form a nice parallelogram in the plane. Okay? I want to find the volume of a parallel pipehead. I need one more vector. If my third vector is in that plane, what's the volume of this parallel pipehead going to be? What would be the vector, if it has a fixed length, what direction would give me the maximum volume? If it's perpendicular, if it goes straight up. And then the less straight up it goes, the less volume I get. What I'm going to do now is called the advantage of the blackboard. Okay, it's much, much nicer to be at the blackboard at this point. I'm going to take this and I'm going to erase I hat, j hat, and k hat. Okay? So I'm erasing them, and I'm going to put in a new vector. What vector do you think I should put in here? How should I label it? What would be a good letter to use for the vector?
X?
Not x. So I've got v1, v2, v3, w1, w2, w3. What should come before v1?
T?
Why t?
T1?
Why t?
It comes before A.
A comes before v. Why u?
Because it's the letter right before.
It's the letter right before. You always want to have good notation, right? When you see a big F in a calculus class, what do you immediately think of when you see a big F? And if my kids get this one, I will be shocked. What do you think of when you see big F? I'm sorry? Integral, right? There's usually a little f lurking in the problem, and big F is the integral or the antiderivative. Why do you have notation like that? So you can quickly glance down and see what's going on. You really want to think about notation. When you have a situation like this, I could put anything I want. I could put t, I could put a, I could put x, but u1, u2, u3 is really good. So now all I'm going to do is I'm going to replace the I with a U1, and the J with a U2, and the K with a U3. Can anybody interpret this quantity? So this is some vector dotted with something involving a cross product. It's U dot V cross W. So these components are V cross W, and this is now just U dotted with that. So this is telling us that the determinant of the 3 by 3 matrix, coming from the vector U, V, W, is the volume of that parallel pipette. And if you think about it, the volume will be maximum, for given V1, for given V and W. If U has a fixed length, you want U to be perpendicular to that plane. And so V cross W is basically giving you a vector that's perpendicular to V cross W. And so if U1 aligns with that, it's going to be maximal. If U1 is perpendicular to that, it will be 0. This is the best way I can somewhat motivate the geometric interpretation for the direction of the cross product, is thinking about what's going on here with this formula for the parallel pipette and its volume. And so this now allows us to calculate volumes in three-dimensional spaces of parallel pipettes. Okay? So any questions on what we've done up till now? So we have a formula for the cross product. We have a geometric interpretation of it. It gives us areas of parallelograms spanned by V and W. We have certain cross product identities. We have ways to prove them. Roll up your sleeves and do a lot of painful algebra. Right? You can actually have a computer program do this for you. And you can have Mathematica do the symbolic calculations. There are actually programs now that will prove binomial identities for you. It's amazing what you can get computers to do. There are other ones where we have some kind of geometric interpretation. Now, the cross product is not as friendly as things that we know. It's not like normal multiplication where order doesn't matter. Order matters. V cross W is negative W cross V. So I brought in an object on the first day of class where order really matters, Rubik's Cubes. This is very similar to that, that order you do things matters. Here is another question. What does V cross W mean? What's one possible meaning of this? So remember, the cross product is a binary operation. It takes as input two vectors and outputs a vector. So give me one way to interpret this.
A vector that's perpendicular to both the cross product of V and U and also to W.
No, you have to tell me how to do the operations.
Oh, okay.
How do I do this?
Maybe you do the cross product of vectors V and U, and then you take that vector that you find.
So one thing is I could take the cross product of V and W and then cross that with V. What else could I do?
V and U.
Actually, that's a V.
Oh.
All right. So do you think these two quantities are the same? Which one do you think is easier to analyze? The second one. What's V cross V? 0. Because V and V are in the same direction, so this is just 0. This is almost surely not going to be 0. V cross W is perpendicular to V and W. Oh, wonderful. It's perpendicular to V. It's going to be maximum possibility. So this tells us, unfortunately, it's not associative. Damn. Right? Order matters. This is very different than most things we work with. So we have what's typically called the right-hand screw rules. Do you think we need to use our right hands? If we're going to use the right-hand screw rule, yes. Do you think you could have created the left-hand screw rule? Yes. Would the notation be a little bit different? Yeah. But since there are more right-handed people, the right-handed people have one. Yep. So you can say they've screwed the left-handed people. All right, so we have I cross J is K. J cross K is I. And K cross I is J. So the way you view it is if I take two vectors, V and W, and I want to figure out what direction is the cross product, you take your right hand, you have your fingers curling from your first vector V to your second vector W, and then your finger points in the direction of V cross W. If you were to do this with your left hand, you'd be off by 180 degrees, unless you then went from W to V. It doesn't really matter which way you do it, but since everybody does it using their right hand, we'll use our right hand. And this just tells you the direction that V cross W will point in. So in particular, if you look at the XYZ plane, you take my finger here, I move from the x-axis into the y-axis, and I'll point up into the z direction. I move from the y-axis to the z-axis, I'll point into the x direction. This will be negative J cross I. So order matters, unfortunately. Okay? So the cross product is going to be extremely useful later. There are a lot of applications of this in physics. So how many of you are potential physics people? Okay. How many of you have seen cross products in physics? Okay, a few. So when you get to like electricity and magnetism, it comes in all over the place. All right. So I'm just making sure I've covered everything that has been asked. Okay. Any other questions on material? Yes.
What again is like the U times the parentheses V times W supposed to mean?
So this is going to be the volume of the parallel pipette spanned by U, V, and W. So V cross W gives you a vector perpendicular to the parallelogram created by V and W, whose magnitude is its area. And then when I look at U dotted with that, it gives me the volume.
Does it make each other like geometrically? It's too hard to draw a diagram.
So, I mean, if I try to draw the picture, so let's see. So I could have three vectors like this, but I really want to somehow convey that this one is coming up. And so then this one would be coming up like this, up like this, something like this, some kind of cube like that. And that's what the parallel pipette would be. And here would be, say, V, here would be W, maybe U. I may have my volume off by a sign. I don't care about being off by a sign. And it's what's the volume of this? And if any two of them are in a plane, that's fine. But if all three of them are in a plane, you're in trouble because now you're not going to have a volume. And so if V and W are in the same direction, you're already dead. If U is in the plane spanned by V and W, you have no volume. And for a given length U, the maximum volume you can get is when U is perpendicular to the plane V cross W, because then the whole thing becomes the height. Otherwise, the height gets decreased by a factor. And that's where the dot product comes in. OK, so let's just do an example of the cross product, and then I will do Morley's theorem. So let's say V is 2, 7, 1, and W 8, 2. So this is in honor of today being E Day. So you might have heard of Pi Day, March 14th. E Day, E is 2.71828. So February 7th, 2018 This is E day. Okay? So V cross W, so I, J, K, 271, 828. So the I component, I'll write it, IJ, 28, it's a really messy 7, 7, 2. So for the I component, I'll get 7 times 8, and the other one will be negative 1 times 2. The J component will be 1 times 8 minus 2 times 8. And the K component will be 2 times 2 minus 7 times 8. All right. 7 times 8 is 56. Minus 2 is?
54.
Yeah, kids. College kids, don't let my kids beat you. 1 times 8 minus 2 times 8.
Oh, wait. Negative 8.
College kids, I'm getting really scared. Come on. 2 times 2 minus 7 times 8.
Negative 52.
All right, so here is an example of a cross product. I want to end the day with Morley's theorem. This is a warning that just because you can prove something in a certain way does not mean you should. And I actually still have in my office a memento of learning this lesson the hard way. So when I was walking to school, to the department one day early in my graduate career, I was with 2 of my friends, and we started talking about Morley's theorem. And I believe it goes back to the ancient Greeks, but I believe it was only first proved around 200 years ago. And it's the following. Take any triangle. So a triangle has 3 angles. Trisect each angle. So you split each of these into 3 equal parts. Right? That doesn't quite look equal. So let me try to do a little bit better job trisecting. All right. So when you trisect, for each side of the triangle, take the 2 trisecting lines that are closest, and that generates a point. You now have 3 points. Connect the 3 points. What kind of triangle is that? Any conjectures? What is it?
Equilateral triangle?
So the conjecture is equilateral. It is an equilateral triangle. The best proof I know is due to John Conway, who starts off with an equilateral triangle and reverse engineers to get you a triangle. I told my friends it's trivial to prove. They go, how do you do it? I said, well, what you do is you write down, you make this point 0, 0, make this point 1, 0, find the coordinates of the 3 points, calculate the squares of the lengths, and show that they're equal. And so my friend bet me, not that I couldn't, but that I wouldn't have the patience to finish this before we got our PhDs. I did not work on this heavily, but about 18 months later, I finally gave him the proof. I was allowed to use Mathematica. I wrote down the equations of the lines. I kept expanding things, clearing denominators. I ended up with with expressions for the 3 sides where they were polynomials in 2 variables of degree, I think, 48. The best angles I found were to use like the tangent of 1/3 of the angles. Really simplified the algebra. And so I have these expressions in 2 variables of degree 48. And I just subtract one from the other, and I tell Mathematica, simplify. And it shows all the terms cancel out, and you get 0. It is a proof of Morley's theorem. He bet me if I couldn't do it, I would owe him an ice cream not to exceed $2.50. If I could do it, I'd get dinner not to exceed $12.50. I bought him the ice cream anyway for teaching me a very valuable lesson. Just because you can brute force things doesn't mean you should. If that's the only way you can do it, do it. But what I really want you to get out of this course is higher ways of looking at things. All right, this is a good place to stop.